Actually, let me see if this spurs some questions. Let's have a quiz on Wednesday. Keyword. And we do it on chapter 4 and 5. Yeah. That's crazy. So that's going to deal with the sum of x, p of x stuff, the binomial probability stuff, and the uniform probability stuff. I'm going to put the formulas on the quiz, so we don't have to worry about formula sheet yet. Let's see if that spurs any questions, even though our brain thinks it's 6 a.m. right now. I hate this setup, I really do. I'm not a projector guy. Yes?
Can you go to 85 on chapter 4 section?
Which chapter?
Chapter 4.
4? Okay. 85. Oh, okay. All right, this is beautiful. So I'm going to do one like that, okay? So let's say I had a situation where there were 30 people, and the probability that they are, let's do this the other way around, why not? That they're, no. So we'll say the probability that they have some problem is 12%. So the probability they don't have that issue is 88%. Okay. I'm feeling like medium creative this morning, apparently. Yeah, some kind of problem. So if I said what's probably that exactly 4 of them have that problem, what kind of distribution is this that I'm working with? What kind of distributions do we know about?
Continuous.
It's not continuous.
It's one of them.
It's one of those. It's one of those that we've dealt with. Sorry? Binomial. There's 2 situations. Either you got it or you don't. You got the problem or you don't. Is everybody with me? So they would have told me 12%, so I had to figure out 88% for the other situation. I got 30 people I'm looking at. What's the probability exactly 4 of them have the problem? So that's a binomial thing. Do you even have to remember the name of this? No. Well, what's the formula look like? True, that's right. Yeah. What's the formula look like? How many people do I have total?
10.
How many? 30.
Right.
And how many do I want to have the issue? 4. So 30. Choose 4. So how many successes? 4. And how many other things? 26. All right, let me stop there for a second. Of course, I don't know what your weekend was like, so it might seem like ages ago that we last did this. I don't know. But does that sound familiar? Are you guys with me? Okay. And then whatever the shit that is. But that's the probability exactly 4. If I do one of these, I'm doing the probability exactly something. But what does this question say? This question says, where did it go? Which one was it again? 85, right? It says at least 4. What does at least 4 mean? In fact, what symbol do I put here for at least 4? What symbol goes with at least 4?
Less than or equal to?
No. Greater than equal to. At least, you have to be at least this tall to ride the ride. This kid? No. You're going to squirrel out of there and go flying. No, let's not put you on there. You guys with me? So at least means that or more. What probabilities do I have to add up to get that? Probability, well, what's at least 4 out of 30? 4. Or 5. Or, oh, God, all the way up to 30. You want to write that formula that many times? No. So, I really, bless you. If the opposite situation requires less work, guess which way we should do it? The opposite. What's the opposite of at least 4? Less than 4. What does less than 4 include? 3, 2, 1, 0. So for that problem, I have to do 4 calculations. I have to put a 3 in this formula, a 2, a 1, a 0. And then what do I do with those probabilities? Well, what's less than 4? 3 or 2 or so I add them. Or means add. So that's how I get that. And then how do I actually answer the question? 1 minus what I get, because I'm calculating the opposite situation. Why am I doing that crazy thing? It takes a lot less frickin' work. Instead of doing 4, 5, 6, 7, 8, 9, 10, up to 30, I'm going to do 0, 1, 2, 3, and then take 1 minus that. You guys, we all know that's how opposite probabilities work. If the probability is going to rain today is 20%, what's the probability it won't rain? Okay, we intuitively know 1 minus one thing is the opposite. We know that. But when we get there, we're like, oh shit, what is it? So the opposite situation. Is it wrong to do it 4, 5, 6? No, it's not wrong. It's just I don't want to look at all that shit, and you shouldn't want to do that. Is that cool? So that's exactly how you do that problem. You got to do that formula for these, and then add them, and then take them away from 1 to actually answer the question. I like it. That's the generalized idea behind the probability of at least 1. Why is that one nice compared to this? Because at least 1, the opposite is none. Then I only have 1 computation to do. This is the same idea. It's just that the opposite had 4 things. Oh, well, that's better than frickin' 27 things. Maybe. Anything else from the homework stuff that everybody is doing and is apparently not having trouble with? Okay, all right. So, if there's no other questions, last time we did this sheet that, of course, probably didn't bring copies of, but that's too bad for me. Yeah, I didn't. Yes?
Did you also get 12 in the uniform distribution breakdown?
Oh, shit. Nobody reminded me. So I've got the sheet on my computer. If somebody will remind me, I can just shoot it out over email. So if you don't really care, you don't have to print it out. Yeah. So I've got it like typed up from a few semesters back. Just somebody has to remind me. I don't know, you guys remember the uniform probability formula had the 12 in it? And I love how everybody's like, why is it 12? And nobody asks, why is it b minus a squared? You know, because 12, we can get 12, but why is it there? All right. Maybe. You guys doing all right? I mean, I'm worried about you guys. You guys doing all right? You're here. That's good, because there's like half the class not here. That sucks. They'll come here at 8, maybe. I don't know. Oh, dude, I didn't realize. Shut up. All right. So if there is no more questions, we're going to get into chapter 6. But let me do this first. I'm a little concerned that there's no questions. Do a quick little review. What was the idea with uniform probability? Actually, let me go back even further. We just did a binomial problem. What do I do in this situation? How do I get the mean? What's the formula for the mean in this situation? When they give you a table, has the values and the probabilities of those things, what's the mean?
The Sum of x p of x.
Sum of x p of x. I like. Right? So you multiply the value by its weight. So if I just, let me give you like a really quick problem here. So why is that a valid distribution? Why is that distribution valid?
It adds up to 1.
Adds up to 1, and?
Each one individually is less than 1 and greater than 0.
Beautiful, because real quick, don't even write this down, but if I had this, do those add to 1?
Sure.
Yes, they do.
Yeah.
But 250% chance and negative 150% chance, that makes sense. Those are not between 0 and 1. That's why I have to say both. Because that can make one happen and the other one doesn't happen, so they both have to happen. Even though I know it's kind of like, duh, but still, it's duh. So you should be able to say it. Right? So if I say, verify this is valid, don't just say them, check them. I think I told you. I'm almost certain I told you. Does anybody remember what I told you I was going to do to you? Yeah. I'm going to make it add to 0.9999 or 1.0001. Maybe not on the quiz, but for damn sure on the test, I'm telling you right now I'm going to do it. And somebody's just going to write this. And I'm going to take points out. I'm like, you didn't actually check the damn thing. You know? It's one thing to memorize what's supposed to happen. Check it. If you do get this, is it wrong? Is it like you can't do it? Because that's approximately what? 1, which is what it's supposed to be. I like it. That's what you would say. Or if it was 1.0001, you'd say that. You'd say, I can still keep going. It's due to rounding. And we're humans. We can deal with that shit. Right? Maybe. All right. Now this one, this hopefully is stuck in some of your brains already. The standard deviation, the variance formula maybe is a little bit worse, but it's that guy. And the most common mistake is to forget to square the poor little mean. It's not really fair. We squared these things, we should square this dude too. Now, in the homework that I've looked at, which is not much, in the homework I've looked at, people weren't creating these correctly. What obviously goes here to calculate this? Yeah, xp of x. What goes here, though, to start to calculate variance? Again, how do you tell? Cover the sum symbol, and then what do you see right after it? Is that involved in the sum?
Yeah.
No. What would order operations say to do here? What's the last thing order operations would say to do in this statement? What's at the S end of PEMDAS? Subtraction. I'm going to do that last. I'm going to add these things up. So I need a bunch of these things. And then I'm going to take away the square of the mean. So I need a bunch of these things. So I can add them up and put that number there. Right, everybody remembers, please excuse my dumbass son? Or, that was the biggest reaction yet. Right? So I like to say, addition and subtraction, those are at the ass end of PEMDAS. So you do those last. I love it. All right. Okay. And then we got into, let me leave that up there for a bit. We got into continuous distributions. And really the type that I focus on in that chapter 5 is uniform. The chapter also discusses exponential. And then, to be honest, I mean, if any of you happen to go any further in statistics studies, you get distributions that are, like I said, triangular or trapezoidal or whatever. Then how do you calculate probabilities? You find areas. So you draw it, you see what the area geometry needs, you know, what geometrical formula works for this, and then you do it. And then, of course, you go into calculus shit, which we're not going to do. Right? But for us, I focused on uniform distribution. And what do I need to know to figure out the height of this thing? We have to put on there so I can figure out how tall it is.
Or the distance.
Yes, the distance. I love it. So if I went from 28 to 41, how tall would that be? One over 13. So that the total area would be 1. Now remind me, why does the total area need to be 1? What does area relate to? That also needs to be 1. What does area relate to here? If I find the area between 30 and 40, that is the what that it's between 30 and 40. Probability. So area relates to a probability. I love you guys. If you draw the distribution, it could be triangular, it could be square, it could be normal. If you draw it, the answer to any probability question is just related to the area represented. That's, do you guys even start to understand how that's kind of like, whoa, that's beautiful, that's awesome. You don't have to say beautiful, but I don't blame you. So how would I do this, by the way? How would I figure out this probability? (1/13) times 10. Where 10 come from? Of course, that's just the width, right? So it's width times height to get the area. Beautiful. I love it. So today, what we're going to do is, if I have a shape like the normal distribution, do I have geometric formulas to get areas that one side of it looks like a curvy dude? No. This. Easy. If you don't think it's easy, you're looking at it wrong. It's just areas of rectangles. That's it. Right? You guys with me? And this step right here, when we figure this out, that's called standardizing it. Making it add up to 1. Okay. So, can I do a problem involving the normal distribution just as easily? No. In fact, what is the only thing we know currently about percentages in this picture? Can anybody tell me that if I have a normal distribution, what percentage is there from -1 to 1 standard deviation? 68%. So we do know something, just not much at all. We know 3 things. And let me see if we can play with those things. So there's 68% in here. How much within 2? Anybody remember? Within 2, 95, yeah. And then if I go out to 3 steps away, I basically caught almost everything. That's going to be 99.7%. If I have a normal distribution, I'm going to catch 99.7% of the data if I go up and down 3 steps. So think about it. For height, okay, here, let's do like a concrete example. That's always nice, Jeff. Please do that. I hear. Heights. So this is the really boring follow-up movie. Heights of men in the U.S. They have a mean of 69 inches and a standard deviation of 2.8 inches. At least the last time I checked. With the recession and all that, it's actually probably gone down. We are backtracking a bit, but oh well. So make sure you guys can get this. And these are normally distributed. So I know it looks like this. What's going to go right in the middle? 69. There you go. That's the average. It goes right in the middle of a normal. Normal is symmetric. The mean equals the median equals the mode. All that kind of stuff. Right? So that's 69. Can anybody tell me what heights are up one and down one? Darn it. I always forget to make sure. All right. Yeah. How do you do it? How do you go up one step? You just add 2.8. What are these numbers that I'm putting down here in parentheses? What are they? Statistics idea. What is 1? You can do this. You can do this. What measures the number of standard deviations away from the mean I am? What measures that? The number of standard deviations. Z-score. I love it. Those are Z-scores I'm putting down there. So 1 Z-score would mean I'm 1 step up. -1 would mean I'm 1 step down. So I just add 2.8 and subtract 2.8. So what percentage of U.S. men are between 66.2 inches and 71.8 inches tall? 68%. I love it. See how tall that door is? Or that one? Nobody's looking, but it's okay. You guys came in through the door, so you know relatively how tall it is. How do we know how tall to make those? Well, within the constraints of anything else, if I wanted it to be as short as I could get it, but still have like a certain percentage of men that don't have to duck, like I want 98% of all men to not have to duck, I could figure out, well, what height would have 98% below it. So only 2% would have to be like, okay, see, like, boom, they have to be careful. Right? Me, I'm okay. I'm like right at the average. So I'm like, woo, right through there. You guys with me? So if we were all hobbits, we would have very different layouts, obviously, right? And no shoes. It'd be really weird. Okay. You guys start. You with me? You with me? So I tried just now to give you an exact, concrete, real-world application. How tall do I make a door? Right? If I make it this short, what percentage of men will complain because they have to duck? Now, why am I not bringing women in? Because the tallest men are mostly much taller than the tallest women, right? On average. Now, some women, very, very tall. My God. So, but if I just look at men, I should capture the women too. You guys with me? Maybe, right? Just the way things are. Okay. I like it. Now, let me go further with this. What would be one more step up and down? What height? What would this be up here? Say again? 74.6. And what would this be down here? 63.4. And of course, between those two would be what percentage? 95. I think you said that. So can anybody tell me? Take a minute. Let me put up here what we've discovered. So here's 68%. Here's 95%. Can anybody tell me the probability that a dude is taller than 74.6 inches? Don't say anything out loud. Bless you. Think about this. From what I've drawn, can you figure out what percentage of men are up here? Don't say anything. Bless you. Oh, you're allergic to that statement. Let me check. Don't say anything. All right, we got you. All right. Now, I love you guys so much. This is just a visual little picture. This is nothing even statistical, really. It's just, can you reason this out? Well, if there's 95% in there, what percentage is outside? 5%. So what percentage is on that side? 2.5%, because this is symmetric. I know that it's cut in half on both sides, right? So there must be 2.5% of men So if I made my door 74.6 inches tall, what percentage of men have to duck? 2.5%. And if you can live with that complaint rate, possibly, right, then you do it. You can imagine a lot of things. This is related to, like I said before, how many people do I overbook on a plane? What percentage complaint rate can you handle? Going to bump people. Going to first go, we'll give you $200. We'll give you $300. Well, shit, we're just going to pick people now. Ah, damn. Right? Have you guys ever experienced that? When you're flying? No? All right. You don't want to.
Eventually they just start beating people.
Maybe. All right. Maybe. So what we're going to do today, this is really weak. What if I said, what's the probability that, so this was 2.5%. What's the probability that a dude is less than 67.5 inches tall? Can I get that number from what I know? What are the only values for height that I can give you we can actually work with? Any that land on whole number steps away. Let me see if you guys can do this. Can anybody tell me the number of standard deviations away from the mean that 67.5 is? What's another way to say that? I want you to calculate the Z-score for 67.5. What's the Z-score formula again?
X minus X bar over the standard deviation.
I like it. So this is a population of dudes. But in general, yeah, you're right. The my data point minus the middle divided by the spread. Always. It never changes. We're going to have multiple Z-score formulas, but I'm going to claim they're all the same. Because I'm crazy. So can you calculate the Z-score for 67.5? Don't say it out loud. See, nobody writing. You guys, if you are human calculators, you're freaking me out. So let's see, 67.5 minus 69 over 2.8. So it is negative 1.5 over 2.8. And whatever the shit that is. It's a little over 0.5, I think. Negative
0.5357.
So 0.5357. We're going to start rounding these to two places. You'll see why in a minute. I really want this. So it's a little more than half a step down. You guys with me? It's a little more than half a step down. And that has not a damn thing to do with empirical rule. So if I needed to know the percentage of dudes that are less than 67.5 inches tall, I don't have the ability to do that. And what's the geometric thing look like here? Here's 69, here's 67.5. So it boils down to, can you find the area of this shape? No. You have to use calculus for this, but I'm not going to freaking teach you calculus. What I'm going to do instead is this, which you will left. This is the first in a series of tables that we will use. And I know, and I don't give a shit, that some people use the calculator to do this. I don't care. You still get something out of working with these tables. You get a better intuitive feel for how this thing is distributed. Sure. So don't worry. Let me get this out first, and then we'll talk about how to read this thing. Oh, yeah. Please please be nice to these. Do not write notes on this. Put your name on there if you want to. You're going to use these for tests and quizzes and stuff. I will look at them, so don't put notes on there. You're not allowed to have. All right, so let's do a couple examples. Let's figure out how to read this thing, and then I'm going to unleash you guys on a worksheet. Standard operating practice. Turn this sucker on. So let's before I do this last one I just talked about, let's recapture this idea. Somebody help me out. If there's, let's take a step back. I want you guys to buy into this chart. Whatever this chart's talking about, it better match up with what we know to be true already. So what do I mean by that? I mean, if there's 68% within one step away, what percentage is down here below -1? Say again? 16%. Yeah, 16. How'd you get it? Well, what percentage is outside? If there's 68% inside, there's 32% outside, which means there's 16% on that side. I love it. So if I look up -1 on this chart, it better lead to an area of 16%. So look, the top of this chart tells you how to use it. When you look up a Z-score on this chart, it's going to tell you the area below that Z-score. Now, how the hell do you read this thing? It looks funky as shit. All right? Out here are Z-scores. And here are areas. See why I wanted to get you used to doing 4 decimals for probabilities. So if I wanted to look up -1.00, I would look up -1, so get it to the negative side, -1.0, and then this is the second decimal place up here. Do you guys see that? So if I went -1.00, I do -1.00. And what do I get? 87. If I round that to 2 places, I get 16%. Kicking Z acid. So what this is empirical rule blown up. So now we have much more precise information. I can answer much more precise questions than I could before with empirical rule. So let's try a couple more out. Transition totally. So up here. So say I want to know the probability that Z is less than 2.07. And I have a normal curve. Can you draw that situation for me first? What goes in the middle for Z-scores? What does the mean always become when I make it into a Z-score? Because what's the Z-score mean? The number of standard deviations away from the mean. So what does the mean become? 0. Shit, it's not any distance away from itself. So in the middle of a Z-score picture, you put 0. Yeah, it's gonna jump. Draw this sucker. Whoa. What I love is if the Z-score was negative, where would I put it? Below this. Yeah. So this is a normal number scale, right? It's a normal number line. People put things just wherever they want to, which gets a little crazy. You want the visual to help. So 2.07 will be way up here. So I already know the answer should be kind of relatively big. Right? What percentage is below 0? 0 does what? Cuts it in half. So what percentage is below 0? 50%. So what percentage below 2.07? Much bigger than 50%. So if your answer is 0.017, you did something wrong. The visual should be helping you see to make sure that the answer makes sense. So let's see, can you look up 2.07 on that chart? So you're going to look on the positive side. 2.0 and then 7. 2.07. I get right there. So what you guys got? 9808. So 98%. A little over 98%. So 0.9808. Okay. See how I put areas up top, Z-scores down below? Because Z-scores are evil. They look like probability sometimes. A Z-score of 0.34, you could say that's 34%. No, it's a freaking Z-score. It's not an error. It's not a probability. So put areas up top, Z-scores down below. What about this one? Try to draw this guy here. I don't know how some of you guys do it. Some of you guys don't do any notes. It's weird. But, whatever works. So we want to draw this. It's a Z-score situation, so I know the middle is going to be 0. The middle here wasn't 0 because it wasn't a Z-score. It started off with what we call raw scores, real life score, and then I can convert it to a Z-score. So where's 0.92? To the right, I like it, somewhere up here. And then shade in the area that you want. If you look up 0.92 in the chart, will you get the right answer? What is the chart? Now I'm going to say this so many times. Some of you will go insane, and some of you will never hear me. When you look up a Z-score in the chart, it gives you the area below what you just looked up. So what do you immediately do when you look up a Z-score in the chart? You mark it on your picture below what you just looked up, and you step back and say, did I just answer the freaking question? No! What do you get when you look up 0.92? What's going to suck for you, remember, what's this, 0.90? 1, 2, right? That kind of sucks, but you got 0, 1, 2. So I get this. 8212? So where does that go in the picture? Down here. Does that answer my question? No. Shit. So what do I do to answer my question? What do I want? 1 minus that. Kick ass. And you see how that's, oh shit, there's the 1 minus thing coming in. Of course, that's the opposite of what I want. So I do 1 minus that. Have I shown you this before? I know we've invented calculators. I do realize that. But to do 1 minus any decimal, you make them all 9. 1 makes 8 9, 7 makes 2 9, 8 makes 1 9, you make the last one 10. Or you just put it in the calculator. Maybe. I don't know. So of course, on one level, we're just learning how to use the chart, right? On another level, we have now advanced a huge step. We can answer any probability question related to a normal distribution. If I have a normal distribution with probability questions, all the answers are just waiting for me to go find them. That's Neat. How did we make this chart? Calculus. So you don't have to know calculus, you just have to use the answers. I like it. Calculus says you're welcome. So that's the answer for that one. We do another one here. This is going to get interesting. What if I want the probability that, you can do it, Jeff, 0.18 is less than z is less than 3.01. So z between 0.18 and 3.01. Try to draw that situation. So this is going to be a little different than what we're used to. 0, here's 0.18, here's 3.01. The actual scale doesn't matter. I just want a quick visual anchor to help me do this problem. Here's the area they want me to get. So I already know the answer should be less than what? Less than 50%. Less than 1, I like that. I like that. That's really going out on a limb. I think less than 100%. Wow, very interesting. How much research? How the hell do I get this shit? I mean, the chart has nothing to do with this kind of area. Damn. If I look up 3.01, is that the answer, or is that bigger than the answer, smaller than the answer? It's way bigger than the answer is supposed to be. Exactly how much bigger? You can see, I get the area I want plus extra shit. Exactly how much extra stuff?
0.18.
Yeah, whatever's below 0.18. So what do you think I should do?
3.01 z-score minus 0.18 z-score.
I don't know if you mean this, but you never subtract z-scores. Because that would change where you are on the picture.
Well, like the z-score. Like
The area.
Yeah.
The area. I like it. So we have z-scores, and they lead to areas. Look, so you subtracted the areas. So look up 3.01, look up 0.18, subtract them, and that gives you the answer to the question. Go ahead and do that. We have to subtract those two to get the area between, isn't it? It's not too bad. So playing around with this chart, it only answers one question, which is why it's just one piece of paper both sides. It would be multiple volumes if you wanted it to handle every situation. So we just have to go, oh, if I want between two z-scores, I look at both and then subtract the areas. Not a big deal. So, of course, when you subtract those, what do you get? You get 4273. Sweet. So then there's about almost 43% between those two z-scores. What do those z-scores represent? This is really where it gets a little freaky. Those z-scores could represent life expectancy of dolphins. Those z-scores could represent shoe sizes. Those z-scores, any damn thing. Once I take whatever the situation is, the heights of men, the weights of backpacks, the miles per gallon for cars, once I make them into a Z-score, they all work with that chart. If they're normally distributed, right? If it's not normal, I can't use that chart. So obviously, a big part of statistics is, when is it normal enough? That would be one of the next big questions we're going to answer is, all right, when am I allowed to do this shit? Because it's got all the answers sitting there if it's normal enough to use it. One last example I want to give you, and then I'll give you this handout. I'll tell you in advance, this is a backwards problem. So can you find the Z-score for P19? Anybody remember what that notation means? Big old P sub 19, what does that represent? I love it. 19th percentile, I like it. Which, if I have a normal distribution, what would that look like? Well, so what is that 19%? Do I put a 0.19 down here? Is that a Z-score? It's a percentage. So it's going to be an area on the picture. Where is it going to be? Where is this answer going to be? Because the mean would be the what percentile? The mean has what percentage below it?
50.
50. So that would be P50. So where should P19 show up on the picture? Yeah, down here. It's only going to have 19% below it. So here's 0. P19 should be down here somewhere with just 0.19 in its, I'm going to go ahead and say this word, in its tail. It looks like a little tail, right? Job of the Hut. Oh. Here's his tail. Sorry. We're going to have a distribution later. Oh, good. We'll have a distribution later that looks much more like Job of the Hut. That's what we'll do for now. So, all right. I know the area. I know the probability, which is where we were ending earlier. So how do I figure out the Z-score for this? Yeah. Where? In the body. 0.19 is an area. Doesn't it look like a Z-score? Don't you want to, some of you guys want to do 0.19 and just put the answer down, but that's silly. It's not a Z-score. It's an area. I got to look at the body. We already know it's negative. So go to the negative side. What's the closest I can get to 0.19 in here? Yeah, it looks like right in here. You guys see that? Let's see if you guys can get this. How far away from 0.19 is this one? 6. I love it. How far away is this one? 22. So which one should I use? 6. I like it. And what Z-score does that guy represent? Negative 0.88. Neat. I wish I could say I thought of that ahead of time, but I didn't.
So, should it be closer to 0 than what that shows?
Oh yeah, definitely. Definitely. And like I said earlier, I'm not going to make you know precisely what the scale is and where 19% should be.
I just didn't know where you put it. So.
I don't know. I wasn't thinking. The main thing was I knew it was negative, which helps me know which side to start with, right? Okay, so let me give you this. In fact, I'm going to force you to do this. Well, first thing, real quick, let me take care of this first. Anybody need to borrow a calculator? We'll need a calculator. Just going up if you need a borrow a calculator. Bring your ID. Make sure if one of these is almost dead, so make sure you got battery. That one's the one that's on. It should have battery. Ooh. I'm going to have to take a break. Leave somewhere. Make sure it's got battery. Go to Amazon. Go ahead. So find at least one other person near you and get, okay, we're gonna help each other out through this. If there's an odd man out, we can have 3 people together. You can turn around. Whatever you got to do, you can have 3, that's fine. There we go.